Greetings, everybody. This is our fifth video lecture, and I'm going to talk about what we covered last week. So primarily we talked about two things. One, we talked about CodeMill and recursion in CodeMill, and the second thing that we talked about is microprogramming. So let's just start with CodeMill. Now we wanted to do recursion in CodeMill, and we picked ourselves the Fibonacci recursion as an example. So just to refresh our thoughts, the Fibonacci sequence is this linear combination of the previous two Fibonacci numbers into the present Fibonacci number, where the first two Fibonacci values are initialized to 1. And thus you could use this recurrence to compute the subsequent Fibonacci numbers, which would be like f3 is equal to 1 plus 1, which is equal to 2, f4 would be 2 plus 1, that would be equal to 3, and so on all the way up to, I computed here, f10, which is equal to 55. So you continue in this sort of fashion. So in a high-level programming language such as C, Java, C, C++, you could easily express this by way of a function such as this one here, and you can call it from the main program. And this particular version of Fibonacci in C simply checks if n is less than or equal to 2, in which case it returns 1. If it isn't, then it simply returns the prior two values added together. So that's as simple as that. So the CodeMill version of this is not really that far off or that far away from this representation, except we need to use CodeMill's own instruction syntax. And so the first thing that we do is to identify the registers that would be related to the values in this recurrence. So what we do is we actually associate f of n minus 1 with R2 and f of n minus 2 with R1. And then the n itself becomes R0. And of course, R2 is where we would accumulate Fn, so R2 is also associated in a way with Fn. So you could think of R2 as really corresponding to Fn and Fn minus 1, whereas R1 is Fn minus 2. So what we do, as we did in the C program, we initialize the values of these registers to n, 1 and 2, 1 and 1 rather, the previous two values, and then call the Fibonacci sequence, or the Fibonacci subroutine. So when we call the Fibonacci subroutine, which I think Microsoft Word might have just, or PowerPoint might have capitalized this for me. Just fix that. And so what we have here is then the subroutine itself, which is very similar to C in this situation. And what we do is we check to see if n, which is R0, is less than or equal to 2, in which case we go and then return R1 equals 1, and then RTS. Now, since we initialize R2 to 1, and that's what we really produce as our function n, we also get to have 1 in here in this particular case. Now, if that's not the case, if that's not what we have, which is to say we have an R0 which is greater than 2, then we decrement it and then save it, push it to the stack, and now we want to go out and compute the prior values that we want to have to piece together to compute Fn. So we call the Fibonacci sequence, subroutine itself, to compute Fn minus 1. After that, we pop our n, which we had decremented, and then decrement it again to get n minus 2, and then jumped jump to Fibonacci function again, or the subroutine. And then once these two things have been computed, as you can see, these two calls would have generated us fn minus 1 and fn minus 2. Now we add the two together and then return. And this is basically it. This is what's going to compute this function exactly as it is written down here, where R2 is where we accumulate values. So here's an actual code that I've run here, and you can see that there's a 55 in there for n equals 10. And so I guess we also did this in class, and you know how this works. Now the problem, of course, with this is that, as I've stated here, the very function that we base this on, which is the C function, which is also evident in the code mill itself, makes two calls to compute the next value of Fibonacci sequence, the next number. And so each call spawns two calls, and that, of course, is done for n values. And that would simply mean that we will have to have 2 to the n calls to deal with. And we're not really truncating any of these calls. They go full force. And so this makes it extremely time-consuming. And then we talked about how to reduce the number of calls to something that is more like linear function of n. And then we introduced this Fibonacci 2n, which is like a function that calls itself only once. There's just one minor problem here. I'm going to change this x to n. And now you see that what we do is, if n is equal to 2, again, the same interpretations are given to these variables R1 and R2. R2 is the actual function that we return. And so if n is equal to 2, we then return 1 into R2. This is a global variable. We don't really return it when we set it to 1. And if that's not the case, then we actually call Fibonacci n minus 1 prior. And you see that there's no n minus 2 in this situation. And then after that, we add R2 to R1. And then we switch them around. We basically swap R2 and R1. This is what these steps do. And then call the function again. This is what we did in CodeMill, and this is the C version of the same. This is sort of typically called a tail recursion, but to make it completely, to put this thing into a tail recursion form, what we could do is we can actually bring the R1 and R2 into the argument list of Fibonacci 3, which I call here in this case, and now let these two variables basically help us do the swapping. This is just the prototyping of the function here, but the actual function is defined here. So we say if n is equal to 1, return R1. If n is equal to 2, return R2. Else return Fibonacci 3, and then just make n equal to n minus 1. And then what was R1 now becomes R2, and what was actually R2 now becomes R1 plus R2. So we kind of do this addition right inside the argument of the Fibonacci function. This is really tail recursion. And we pass these computed values by tailing effectively by just truncate the second call and doing the addition in place. So with this, now you could see that the number of calls is really reduced to n, because n will be reduced to n minus 1, then on to n minus 2, etc., and so on. And so this thing will call itself only n times. And so with this, now we have the CodeMill version. And what we do is, as we did in the C version, we initialize R0 to, by the way, we call this Fibonacci with n and 1 and 1. So this is how we actually start this whole process. And so we really, it's almost like iterative in a way, because we have the initial values set, but the function calls itself, so it is recursive. That's for sure. Okay. That the next value of the Fibonacci is computed recursively within the function by having the function call itself from within, but we initialize these R1 and R2 to 1, so that the function, when it actually begins, will have a set of values to go with. So the rest of it is in code mill identical. Now R0 gets set to n, and then the other two are set to 1. I guess I should have set that other one to 1 as well, but I'm actually doing it slightly different here. I'm not really returning R2 or setting it to 1 here, but I'm going to do it within the call itself, which I could have done here as well in the C version. In other words, I could have just returned in this situation, instead of like setting them separately to 1 and 2, I could have said if it's less than or equal to 2, return 1, without actually just writing these values as in fact they were passed down here by the function's call here, by the function call that's coming from the main program. So effectively, this exceptional case, which is when the recurrence stops, sets the function output R2, that is f of n, to 1. Otherwise, it decrements the n, value of n, by 1, and then calls the Fibonacci again itself. And then we do the exchange and we do the addition, and then we return. And we talked about how the order between exchange and add instructions here actually makes a difference. If we were to put add and exchange in the other opposite order, then our f of n would have been accumulated into R1. But we want it to be in R2. That's why we made this switch, and we explained that in the class, in the lecture that we had last week. All right, so now, and the code mill code is right here for this. It's basically identical to what we have. And again, it actually, this time I computed Fibonacci 40, which comes out to be a very large number. For this, by the way, I set the register width to 32 bits because it's a very large number. If you use 16-bit or 8-bit setting, then you would not get something meaningful. So make sure that you actually set the width, the scratch pad size, to something that has 32-bit wide registers, and it could be 4 by 32, 8 by 32, or 16 by 32. So I also talked briefly about variations. Now here's one where we actually have f of n equals to f of n minus 1 plus 2 times f of n minus 2. So same ideas can really be used here. So we take the same template which we had for the case that exact Fibonacci sum. Now in the recursive call portion, we again decrement. This is a single call version. Decrement R0 by 1, and then we jump back to Fibonacci. On coming back, first we shift R1 left just to multiply it by 2. Remember now, our association was R1 is equal to, R1 is really f of n minus 2 here. So let me just make a small change. And with that association, of course, that's what we're doing here. And then we exchange R1 and R2 and then add. So this is basically a simple addition here. That is simple insertion. Just one other instruction comes in. The rest of it is identical. That shift, of course, comes about because it's equal to 2 times this. And we can always achieve that by shifting what is in R1 by 1 bit to the left. So that's really what it is. And, then towards the end of this video, I'll assign you a problem that will be somewhat similar, and then you will be doing that as part of your homework assignment. So this is the actual code. This time apparently I'm computing this thing for n equals 10. Of course, that's not going to come out to be 55 because we have this 2 times f of n minus 2. You can always compare, by the way, what CodeMill generates with what you would generate in C to check your answers to see if in fact they come out to be the same. Now, the second topic that we took up was microprogramming. So microprogramming was really the name of the game in the computer architecture world in the 70s and 80s. Lots of machines came out with microprogram architectures within. And just like we did explain in class, machine instructions were basically executed by microprograms. And so the RISC architectures introduced in the 1990s sort of, I guess you can say, muddied the water a little bit. And because of the critical timing issues that they had, that each instruction be executed in one clock cycle kind of necessitated what we would say a hardwired controller option. But microprogramming really has made a return in a way, because a lot of the ASIC applications, application-specific integrated circuit chips make use of microprogramming. And on top of it, complex instruction set computers such as Intel chips also rely on microprogramming, because they have instructions that take many clock cycles to execute. So microprogramming is actually healthy and alive. Now, here is the microprogramming architecture that VESP has been extended to. And what this really diagram demonstrates, I hope that you get this, that there are two memories here. One is where we normally execute our machine instructions in VESP, and all of these are still handled by the critical control registers that we had, like program counter, and then the instruction register, and then the memory address register, etc. But the other memory is for our microprograms. That's where we store our microprograms. And so the process is as follows. We created a data path with a 3-bus structure, where our operands are loaded onto 2 buses at the top of this data path, which is called A bus and a B, which are called A bus and a B bus. And then they are driven through the data path into this so-called third bus that's so-called O bus. And that O bus then returns whatever value it has, whatever that is on the O bus gets returned to one of the registers in here. And this includes all of the registers, including the control registers we have. So the mechanism for putting something on the A bus, putting something on the B bus, and selecting a computation operation through this data path, and then finally computing into the O bus, and finally putting that into one of these registers, all of those steps are orchestrated by the microprograms that we write and store in the microprogram memory. So microprograms are basically sequences of microinstructions. And then the microinstructions will have a format, as we shall see on the next slide or two. And of course, we now have a microprogram counter and a microprogram memory address register, which basically sequences, just like this will do the same here for the machine instructions we have, machine programs. These two control registers at the micro level will actually take care of the sequencing within the microprograms that we execute. So here's a microsequencer, and there is this microcontroller which really fetches a machine instruction, which then decodes it, and then it makes a call to the microsequencer. So it's really a call from this machine controller to the microcontroller, which then executes and then returns just the same way that we will return from a program here once the microprogram is completed, execution of it. So really very much the same idea, but now we've gone one more step deeper into the towards the hardware layer, or the ultimate logic layer, transistor layer of the architecture that we are designing here. So this diagram just simply shows you that what is called microprogram controller here. It was the hardwired, with all the flip-flops that we drew, remember, all the transitions, all the little pulses that we generated, one hot assignment idea, that all of that has now been replaced by this controller here. Okay, the rest of it is the same. We no longer have a hardwired controller, but we have a microprogram controller. Okay. So the actual positioning of the various registers of VESP, the microprogram version, are indicated here. Like A register is on the A bus, PC and MAR as well. We also put 0, the ground, on the A bus, and then 5 volts on the A bus as well. So in this case, we put some 5 things in here. And on the other side, we actually have MDR, IR, B register, and IX, as well as 5 volts. And then the output bus. So this is how it's organized. And now we're going to, out of this, we can actually go out and make a particular micro instruction template or instruction format. There are 4 kinds, and we get to use mostly these 2, the first 2. So if the leftmost 2 bits in the so-called micro instruction word are both 0, then we call this a data transfer, which simply means that we're going to take something from and we're going to take one of these 5 things and put them on the A bus, one of these, 5 things, and put them on the B bus, and then select a function and then bring it back to one of these. So that's what's called a data transfer type of micro instruction. And then we have a branch micro instruction, which means that we're going to branch within the microcode that we're executing. And there are 2 other, we get to use this 1-1 option, which is a ROM transfer. Input output is really to get things in and out of the machine level of the layer of VESP, but we don't get to use that much. This could be handy when you're executing, for example, instructions that are related to keyboard and other, peripheral device management, like the BIOS in Microsoft, for example. So the specific formats then are really for the first 2 are like this. If you see 0, 0 on the leftmost 2-bit positions here, that is a data transfer micro instruction. Then the next, the next 3 bits will tell you what you get to put on the A bus. So the A bus would have one of those 5 things that I showed, but I allocated 3 bits. That means you can theoretically select one of 8 objects, 8 registers or 8 things into this particular A bus. Same is true for the B bus. Then you have the function select. These are basically hexadecimal numbers, and then you have the destination select. The branch micro instructions are going to be identified if you happen to have 0, 1 in here, and so the only thing you have beyond that is a branch select condition. That is to say, how would you branch? Would you branch with the accumulator being equal to 0, greater than 0, less than 0, other conditions? This basically tells us what would make us branch. And then the address of the branch. Now the branch addresses are within the micro engine. That is, we're jumping here, not there. So the branch micro instruction would take us from one place here to another, just like the conditional or the forced jump instructions in the machine layer. We have the capability to actually go between micro instructions. So you got that. And then the microprogram program IO would be 1, 0, and then you have to select the routine, and then you have to select an address. These actually can be combined into one, but I just created a space, and this could also be set aside for classification or just clustering these routines. Microstore transfer would be basically 1, 1, and then read-write option here, which is to say you can either read or write in and out of the microstore. And so we will use mostly the read option, not so much the write option. And that's something that we get to use. So basically four classes of micro instructions that we have here, or you can call them 4 types of micro instructions. So I think this is as far as we went last week. And so by way of summary, I'd just like to say that we covered recursive programming in CodeMill and introduced microprogramming. And of course, we'll cover more during week 6 when we get back to class for that. Now, here's your homework assignment. You got basically 2 problems to work on. And the first thing is that you want to write 2 programs, one for each of these 2 recursive functions that I've given you. And I want you to evaluate both of these at n equals 20. The second problem is somewhat different. I had written a program that handles what's called the Tower of Hanoi problem in CodeMill. And the code itself is given to you in the assignment that I actually emailed already. But that works with, I guess, 8 disks. And so I'm just asking you to change that to 10 disks to see if, in fact, it will work when you make the changes. So the code itself is down here. It takes a bunch of pages here. And you have the text version of this, so you should be able to actually copy it from there and then see if you can change it to make it work. So this really brings us to the end of this particular lecture on video. And here's, by the way, the sample run. One of the things that you have to make sure is, of course, the program does this for you, so you don't really have to worry about it as much, is that at any point in time when you're putting these disks into one of these 3 pegs, you should always make sure that the smaller disk is always at the top, on top of the larger ones. So like this will be a legit placement. This will also be the same, and so on. So you could not have the red one over the yellow one, and that would just not be right. So I guess until our next video class, take care, and I'll see you in class on Monday.